Well, hello, everybody, and welcome to International Careers Week with the Montana World Affairs Council. We are so thankful to be joined by Michael Poland today, a USGS volcanologist. Mike is a research geophysicist with the Cascades Volcano Observatory and a current scientist in charge of the Yellowstone Volcano Observatory. That's cool. Can't wait to hear more about that. His recent work has focused on using gravity change over time to understand the character of the fluids that drive volcanic unrest, and also on the potential of satellite data to improve forecasts of future changes in volcanic activity. Welcome.
Thanks very much. I'm glad to be here.
Fantastic. So we have students on the call. Students, I'll remind you that you can type questions in the chat and we will ask Mike. But I'm going to start us off with our first question. And that is, what inspired you to pursue a career in volcanology? And how did you become involved with the Yellowstone Volcano Observatory?
Sure. I think that what really got me into volcanoes was Mount St. Helens. I was a kid in 1980 when it had its really big catastrophic eruption. And I remember following it in the news and learning about it in school. And I was growing up in Northern California. So it was very easy for me. And my dad would take me camping up at Mount Lassen or up at Mount Shasta, more volcanoes. And it just stunned me that, what I saw on TV at Mount St. Helens is something that could potentially happen not that far from where I grew up. And that interest just was there until college. And I took a couple of classes in geology, and that sort of hooked me. Um, as for Yellowstone, that was sort of lucky. I started out my career at the Cascades Volcano Observatory. We're based in Vancouver, Washington, not far from Mount St. Helens. And then in 2005, I moved to Hawaii, and I worked at the Hawaiian Volcano Observatory for 10 years. I moved back to the Cascades in 2015, and I was sort of not quite sure what the next stage in my career was going to be. And then the person that did run the Yellowstone Volcano Observatory moved on to a new position, and it created an opening. And so I was sort of in the right place at the right time, and I had the sort of experience that they were looking for in someone to work at Yellowstone. And it's just been wonderful because part of my job at Yellowstone is to coordinate research on Yellowstone volcanic activity, both past and potential future activity. I get to work with people all throughout the region, scientists at universities, state geologic surveys, the National Park Service, and it's really been wonderful. I've learned a tremendous amount. It's great fun, and I mean, come on, I get to spend a lot of my summer in Yellowstone, and that's just not I'm not going to complain about that.
That's fantastic. So we have a question from students. What is the most interesting thing you've done in your entire career?
Oh man, there's so many things. But if I got to pick one thing, I would say it's eruption response. And so I've been engaged in several episodes of eruptions of volcanoes. Um, the one that I felt most excited by was Mount St. Helens in 2004. Now, many people don't know that Mount St. Helens had an eruption from 2004 to 2008. And it was just a quiet eruption. It built basically a pile of rock in the crater. But of course, as it's starting up, we don't really know exactly what's going to happen. And I was on the mountain helping install equipment, make observations. It was incredibly exciting. I was involved in many eruption responses in Hawaii. And a couple of times, I had to be in a room with hundreds of people that lived in an area where lava was advancing on their community. And I had to talk to people about whether or not their home was likely to survive a lava flow that was headed their way. It was difficult to have those conversations, but I never felt that my job mattered more and than it did at those times. I mean, I do scientific research, I write scientific articles and so forth. Um, in some ways, that feels very esoteric. Does anyone read a scientific paper that I've written? Probably not many people. But that time when I was talking to a auditorium full of people that were threatened by lava, I realized that my job mattered, and it was important. I'd never really felt so involved and engaged in what I was doing as I did in those times.
That's great. Thank you. So another question from our classrooms. What's the most challenging thing you've had to overcome to get to where you are today? And who's been your main support throughout your career path?
Mm. I've had nothing but support over my career. And I would say it starts at home, right? It starts with my family. Um, my parents thought that I was going to be, an accountant or something like that. When I came home one day and announced that I was going to be a geologist, they didn't react negatively, and they've always been very supportive. My spouse has supported the fact that I have to travel. Sometimes I'm out of touch for long periods of time or in the wilderness, um, and hasn't and supports me in the work that I want and need to do. And colleagues, I've been lucky to have a string of mentors throughout my career. And that's something I guess I would encourage, in addition to having support from family and friends. I think it's important to go out and get mentors, and make sure that you've got people you can rely on to give you good advice and help guide you through a career. Because there's a lot of people out there that have the experience that you will one day have, but before you get that experience, it's best to rely on the people around you to help supply that. So I've been very lucky in having good mentors. As for the biggest challenge, that's tough. There's a lot of challenging things that we do. It's a lot of it's learning new things, learning how to write well, learning how to communicate well. I think the communication has been one of the bigger challenges, but it's also one of the most rewarding things I do. I love talking to people about volcanoes, about Yellowstone, about Hawaii, you name it. And it's taken a lot of practice to learn to communicate in an effective way. So that's been a challenge, but it's also been incredibly rewarding.
That's wonderful. Is there a specific research study you have participated in that is one of your favorites? If so, can you tell us about it?
Yeah. One of the things I guess I really liked doing was when I was in Hawaii. We noticed that there was some variation in activity from the big erupting volcano there, Kilauea. It's the most commonly erupting one. And Kilauea seemed to be producing more lava, and it was behaving in weird ways. The ground was deforming in weird ways, and there were different kinds of gas emissions. Now, my specialty is in ground deformation. I look at how the ground moves, and we relate that ground movement back to where magma is located. But in a volcano observatory, Yellowstone Observatory, Hawaiian Observatory, Cascades Observatory, you are with a group of people that have different expertise, but we're all focused on the same problem. So I'm a deformation person, but the seismic person's down the hall. There's a gas person over there. There's a person that studies geology, two doors down. And the power of the observatory is that we're all working in the same place on the same problem. So we get together and we talk these things through. And so when I was in Hawaii, I was involved in a study that looked at the amount of magma coming in from the bottom to Kilauea volcano and the effect that that has on what we see at the surface. And we were able to actually calculate that there was a surge in the supply of magma to Kilauea. It was like somebody turned the hose on full blast, and we were able to back out, we were able to calculate the amount of that surge based on things we were measuring at the surface. We were able to see what was happening tens of miles deep in the earth. And that was the first time that had been done at any volcano on Earth. And so I'm really excited about that work. I'm still playing with that sort of thing, even though I'm, 9 years removed from Hawaii and working on Yellowstone now. I still dabble in Hawaii because it was such an exciting project.
That's fantastic. Okay, day in the life of Mike. What does a typical work day look like? And how much of your time is spent in labs versus in the wilderness?
Um, it depends on the time of year. A typical day right now is in front of a computer. And I don't need to tell you that, winter is not a great time to be in the field. So we typically don't do a lot of field work in wintertime. That includes in the Cascades, but the only place you can do it, winter field work, is in Hawaii, right? Because there's not really a winter. Um, so I spend a lot of my time during the winter months working on reports, answering questions, writing scientific papers, writing proposals, writing plans, corresponding. So I'm very much in front of the computer these days. In the summer, that starts to change, and I spend, sorry, another wintertime thing is having a cold. Um, In the summer, you spend more of your time in the field because, of course, you can get out there. And so I will often spend time doing field work in the Cascades or in Hawaii. Um, and then I, of course, am in Yellowstone. It varies, usually many weeks every summer I'm in Yellowstone, but it varies from year to year depending on what needs to be done. And so when I'm out there, then I get to spend time, hiking, backpacking, going to various sites. Because I'm a geophysicist, so I'm studying seismology, ground deformation, things like that. A lot of what I do is checking on equipment, making sure it's working properly, installing new equipment, working with others that do that. I'm not an engineer by any means, so we need experts that have that kind of experience to install and wire up a seismometer. But I can certainly help with that and help with here's where I think everything should go, and here's how I think it should be arranged. So I think in the summer, we start pushing, a third of the time we're in the field. The winter, it's, about the only time I get in the field in the winter is when I go to Hawaii.
That's great. Can you tell us a little bit about some of the technology and the scientific methods that you use to monitor and study the volcanic activity?
There is so much technology, and I find it amazing, frankly, at all of the cool things that are possible. Um, my field in particular, ground deformation, has been really revolutionized in the time I've had a career. Um, Over the time I've been working the 20, 25, 30 years, somewhere in there, we've gone from collecting the measurements ourselves, which means we go out and we might shoot a laser at a reflector and measure the travel time of the laser, and that tells us whether or not the ground is stretching or contracting. Now we install GPS stations. We cement them to the ground. We hook them up to a radio, and we can get instantaneous positions that can be good down to a millimeter or a few millimeters. And so we know how the ground is moving to a fraction of an inch. We can also see how the ground moves from space. And this blows me away that it works. There are radar satellites that orbit the Earth, and they shoot radar signals down at the Earth, and they bounce off the Earth, and they measure the return. If they do that again, they come back around and they take the same measurement. They can look at the travel time of that radar wave and know whether the ground has moved up or down. So we basically can take pictures of how the ground is moving from space. That's just in deformation. The satellite technology with gas emissions is stunning. We can detect volcanoes starting to erupt based on heat pulses that appear out of nowhere from space, based on different gases that suddenly end up in the atmosphere. So the technological advancements have been stunning. I think they've really been amazing when you look at the satellite technology. And that's only going to get bigger and bigger. But the only thing we can't detect reliably at a low level from space are earthquakes. That requires equipment on the ground. But I kind of think like in a far off world, maybe someday some smart person is going to figure out a way to detect earthquakes from space.
That's great. So I'm curious a little bit more about the ground movement. When you're measuring ground movement, is that before or after an earthquake, or when you detect eruption activity, or is this on a daily basis? Is our ground moving and we're not even really aware of it?
That's exactly what's happening. Most of the places around us, the ground is moving to some degree. Some places it's much more impressive than others. So, for example, I grew up in California, and the Central Valley of California is sinking pretty quickly. It's sinking because groundwater is being drawn from the subsurface. So, as you're sort of pumping groundwater out, the ground sort of sinks down. So, that's something we're able to measure at near an earthquake fault. There's faults all over the place. There's faults in western Montana. When the faults move or when they slide, you will see the ground move. And that's something we can measure in various ways. The reason we are really interested in this in volcano areas is because you can imagine like a magma chamber, we often draw the cartoons like there's a red balloon beneath the ground. And as that magma chamber begins to pressurize before an eruption, the ground will inflate like a balloon that's being pumped up. And then if an eruption happens or if magma drains away and goes somewhere else, the ground will deflate like a balloon that's losing air. So we study ground deformation to see what's going on beneath the surface. Is there fault movement? Is someone pumping water or oil out of the ground? Is there a magma chamber that's gaining or losing pressure? It can tell us a tremendous amount what's going on below our feet. And when we combine that with other information, seismic information or the structure of the subsurface, the geology of the surroundings, you can really begin to tell a story about what's happened in a place and what may happen in the future based on the data you're collecting. I like to think of being a geologist or geophysicist like being a detective. It's exactly like being a detective. You don't say like a crime has been committed, right? You didn't witness the crime, but you can collect evidence. At a crime scene, it might be fingerprints or fibers or DNA or eyewitness accounts, maybe even. Same is true in geology. We can look at the rock composition. We can look at the layers of rock. We can look at what's happening in terms of seismology or ground deformation. And then we reconstruct the story. We're earth science detectives. We try to figure out what happened and what may happen in the future. So it's if you like detective work, geology is really similar.
That's so great. Okay, has climate change had any impact on your work?
It has in a couple of ways. One is it's changed the landscape. So, in fact, just before I joined you guys, I was participating in a series of lectures about looking at the Cascades and how things have changed. And even just comparing photos from the 1920s to the 2020s, you can see that the amount of ice in the Cascades is much, much, much less. And so this changes our ability to install equipment and maintain equipment. Sometimes it makes it easier because we can hike to a place more easily. In other places, it gets a little harder because things are moving in ways that now the ground is a little less stable than it was. So it definitely changes the landscape. That's part of it. In Yellowstone, it's possible that climate shifts may have some impacts on hydrothermal activity. So, for example, you're familiar with Old Faithful. The Old Faithful has a geyser mound, and in the geyser mound, there's evidence that trees were growing. Now, there's no way a tree is going to survive right next to Old Faithful, given all of the hot water that's coming out of the ground. It'll be killed immediately. So the fact that there are trees in the geyser mound suggests at some point Old Faithful wasn't erupting. And we can date the trees, and they come out to a time period about 650 to 800 years ago. These trees were growing. And that corresponds to a period of great drought all throughout the Western US. So it seems possible that when there is really extended drought, some of Yellowstone's geysers may stop. And so that has a lot of us thinking about, well, if we go into a period of regional drought that's really severe, how might that change some of the landscapes where we work all the time? I mean, can you imagine a time when Old Faithful stopped erupting because, frankly, there just wasn't enough rainfall in the region to recharge the plumbing systems? So we think about that kind of thing and how it might impact us. We haven't seen those sorts of effects yet, but the fact that they seem to have happened in the past suggests, one thing that may happen in the future.
That's fantastic. Interesting. So one of the questions we have from students is, what type of certifications do you have to be able to do what you're doing? And I want to add on to that. Are there also opportunities for students that are interested, like internships or summer programs, to help with research?
So the certifications, it varies really widely. I have a PhD. I went through school and I got the most advanced degrees I could because I wanted to lead research teams and research projects. I wanted to be able to ask fundamental questions and then address those questions. That's not the only path to get into volcanology. There are so many different kinds of jobs, and the people I work with span a huge range of experiences. We have a huge number of field engineers. They love building stuff. And they love the challenge of me coming to them and saying, I want to put a gravity meter, which is a very specialized piece of equipment, on the rim of an erupting volcano where there's corrosive gas and lots of rain. And The ground is not very stable. Can you help me do this? And it's a challenge for them, right? Because why would you want to do that? Well, hey, look, I want to make this measurement. Can you help me do this? And so they engineer equipment and installations that allow me to try to answer some of these questions that I have. And so the field engineers, not necessarily trained in geology, although they certainly have interest, but then they have these skills in building things. IT specialists. Everything we deploy these days is a computer. It has an IP address. And so we need to understand networking. We need to understand security. So, I mean, goodness me, if we didn't have a really good team of IT specialists, we would be in trouble. All of those kinds of positions that exist in other parts of life exist within volcanology. So I don't want anyone to think that, that having to go and get a PhD is the only path. There are many, many different kinds of jobs out there and an awful lot of paths to get into the line of work that I do. And in fact, some of the most experienced, skilled people in volcanology I know were basically electrical engineers that installed seismometers on volcanoes around the world and got to know so much that they were easily the most experienced people, volcanologist-wise, in the world. So you don't have to have the advanced degrees unless you want to go into a specific line of work, but you have to have a passion for the problems, and then you bring some unique skills to it. And whether that skill is knowing exactly how to network a whole series of weird instruments or build something that's going to withstand corrosive gases, or go out there and operate some analytical equipment that'll be able to tell you the composition of a rock. These are all skills that you can apply to these problems.
Excellent. Can you speak to internships? Do you offer any at the park?
So there's a lot of different ways to get in and try these things out. One of the neat things about the Yellowstone Volcano Observatory is that we're not a single institution. The Yellowstone Volcano is actually 9 different institutions that we all work together. So it's the state geological surveys of Montana, Idaho, and Wyoming, Montana State University, University of Wyoming, University of Utah, the National Park Service, the USGS, and a group called EarthScope, which is looks at ground deformation and seismic activity all over the United States. I'm not aware of all the possible internships, but all of those institutes offer some kind of internship. Some of them might target undergraduate students. Other might target high school students. So I think if you have an interest in this sort of work, there are opportunities. You just will sort of need to explore, like, well, maybe the Montana Bureau of Mines and Geology will have opportunities for people that are interested in seismology, because they do a lot of work on seismology, a lot of work in geology. And so they would have perhaps opportunity for going out and helping in the summer one of their field geologists do mapping. And this is the way a lot of people get into geology, is they end up following a geologist around for a summer, basically helping carry rocks. That's sort of a rite of passage for a lot of us. And so this is one of the things, and then of course, while you're out there, you get tremendous experience. You're talking to an expert for, days or weeks, and you're seeing places that you would never see if you weren't out there in the backcountry doing this kind of work. So there are opportunities. I can't think of any specific ones that I could rattle off now, but the nature of the Yellowstone Volcano Observatory involving all these institutions means that there are a diversity of opportunities out there.
That's great. So our next question, that was a perfect lead-in, actually. Do you collaborate with other teams at different labs, and what does that collaboration look like? And I'm going to add a question onto it as well. Do you also collaborate internationally?
Yes, I would say collaboration is the key to science. It's challenging at times because, personalities, right? We don't all get along. But you've got to be able to take your ideas to other people and pitch them. Talk to folks about what you think is happening, and accept the fact that you don't have all the answers and all the expertise. And there will be other people that have tremendous expertise that can add on to the project you're doing. Just like being a detective, right? There's obviously going to be collaboration between the fingerprint expert and the fiber expert and the ink spatter expert and so forth. So yes, those collaborations happen, and they are really rewarding, I find. The most fun I have at Yellowstone is when I'm hanging out with the seismologists from the University of Utah and the geologists from the Montana Bureau of Mines and Geology and the geologists from Montana State, and they're telling me things I don't know, and I'm telling them things that they maybe haven't thought about. It's tremendous fun, and that's where the advances happen, is when we all get together and start talking. That happens internationally too. Two of my most frequent collaborators are not from the United States. One is from Italy and one is from the Netherlands. And they have expertise in this gravity technique that I'm really interested in these days. And we get together and we collect data from Kilauea in Hawaii, or the Three Sisters region in Oregon, or Yellowstone. And we look at the data together and talk about it. And maybe I could have a chance to go to Mount Etna in Italy and see how they're working there. Sorry, get excited when I talk about science. Um, the collaboration, I think, is really what drives a lot of what we do, and it's really fulfilling to have people that you work with that you would also consider to be friends, and that also makes it really fun too.
That's so great. So tell us a little bit about the tools that you're using to collect data and what those tools do.
So my tools as a geodesist really consist of GPS equipment. So I put out GPS stations and we look at how the ground moves, that satellite radar technique. And the thing that I'm really excited about, and have been for the last 10 years or so, is gravity. Now, probably a lot of you have taken physics, and you know that the gravitational acceleration of the Earth is 9.8 meters per second squared, right? I know many of you have heard that, and it's a constant, except that's not true. Gravity, that acceleration depends on what's beneath your feet and how far you are from the center of the Earth. The farther you are from the center of the Earth, slightly less gravity pulls. Or if there's something really dense beneath you, gravity will pull more. So let's say you're in an area where there's a very dense deposit of metal, gold, silver, copper, whatever, beneath you. Gravity's pulling a little more there. Let's say you're standing in a place that's very loose sediment, like the Central Valley of California. Gravity's not pulling quite as much there because it's not as dense beneath your feet. So that's how gravity can vary over space, but gravity can also change over time. So let's say you're at a volcano and magma starts to accumulate beneath the volcano. That's adding mass. And that means the gravity at the point above the volcano is going to pull a little bit more. So if we measure the gravity and see gravity increasing at a volcano, it might be a sign that there's magma accumulating. And one of the things I love about gravity, this is something you might also have heard in a physics class, is that mass is conserved. So the example I'll give you is, think about a scuba tank. If you pump some air into a scuba tank and then weigh it, and then pump a whole bunch more air in the scuba tank and weigh it, you're going to get a different weight because you've added mass, you've added air. But the scuba tank is not changing shape. So the best way to understand how much air is in a scuba tank is not to look at the size of the tank, because that's not changing. It's to weigh it. That's what we do at volcanoes. I'm into basically weighing volcanoes and trying to understand whether or not their weight is changing. And if it is, why? What's driving that? So I'm really kind of obsessed with that right now, possibly in an unhealthy way. But it also gets me out into the field collecting cool data. And I see really, really neat things. I have observed gravity changes associated with eruptions in Hawaii. I've seen gravity changes in Yellowstone that are related to water. Sorry, water moving around in the subsurface. One of the things I want to do, hopefully in the next few years, is look at gravity changes associated with geyser eruptions, so we can see water moving around in the subsurface. I don't know, it's me geeking out on physics, but that's sort of what I do.
I think that's fantastic. It's wonderful to have your passion. Okay, so given the unique challenge of studying Yellowstone's volcanic system, how does the observatory address scientific uncertainties and then communicate those findings to the public?
Well, that is like the ultimate question, isn't it? Uncertainty is really, really hard to communicate to the public because no scientist ever wants to say, absolutely, this is the answer or that is the answer. And so you'll hear a lot of scientists, and I'm guilty of this too, say things like, well, we have a high degree of confidence that this is true. We're fairly certain that that will happen. We feel very good about this or that, and you put in these weasel words to, I don't know that we've really solved that problem because the same is true in any discipline, right? Communicating uncertainty is really, really hard. And some of the ways we do it are to say percentages. Well, there's a 99% chance that, it's going to rain tomorrow or not. But what does that really mean? And one of the things that cracks me up is, you always leave yourself that out, right? There's a 99% chance it's going to be sunny tomorrow. Well, when it rains, you can say, well, that was the 1%. That happens. Once out of 100 times it happens. It's true. So I don't know that we have a good answer for communicating uncertainty. It is the biggest challenge I think we have in scientific communication in general. And I feel that in Yellowstone too, because the questions I get from the public about Yellowstone really relate to these sort of fantastical documentaries they see online or YouTube channels that claim that Yellowstone is about to erupt and people asking me what I think. And I have to say, no, Yellowstone's not going to erupt. That stuff is all garbage. And then people want to ask, well, what are the chances that Yellowstone's going to erupt? The way I try to characterize is not to give some statistic, which I think is sort of meaningless, but to sort of explain it in ways I hope people can understand. And I think this is something we need to do better as scientists, is communicate at a more understandable level. But let's say there is a chance of that you could be struck by lightning, right? I mean, there is some statistic out there that says there's a 1 in blah, blah, blah chance that you'll be struck by lightning. What are the odds of getting struck by lightning on a beautiful sunny day? Not high, right? Versus a thunderstorm, which is probably a little bit higher. That's sort of why I say we're in Yellowstone. Yellowstone right now, in terms of its eruptive potential, it's a beautiful sunny day. We're not worried about a lightning storm. There's some statistic out there that'll say that it's possible. I suppose it is conceivable that you could get struck by lightning on a cloudless day, but it's pretty unlikely. And so I like trying to express it that way. I think that's a way we could probably communicate better.
That's great. You've touched on this a little bit, but I want to ask you a really specific question. How big is your team of people that are helping you collect data, and who are those people that are on your team?
That's a funny question because if you look at observatories, like volcano observatories in the USGS, Yellowstone's unique because it's this consortium of institutions. The person who's in charge of the Cascades Volcano Observatory oversees a staff of like 50 people. I oversee a staff of basically 0 because I don't supervise the scientists at the University of Utah or the experts at the Montana Bureau of Mines and Geology or at Montana State University. But I work with them. And what I try to do is make sure that everyone is working together well on problems that are important. So I try to basically steer the ship, but I'm not giving any orders to anyone. And frankly, I like that. I enjoy the fact that I'm working with a team of independent people from Montana and Wyoming and Idaho and Utah and various places around the USGS who have one goal in mind, and that's to better understand how Yellowstone works in a geologic sense. And we all have different tools and areas of expertise and areas of interest. But when we get down to it, we all have that in common. And so it's pretty easy to sort of take that energy and direct it towards problem, whether it's understanding how geysers work or trying to understand the eruptive history of Yellowstone. So I get to work with folks from all these institutions in Montana specifically. Madison Myers at Montana State University is an amazing geologist, and she has a whole team of students that work on Yellowstone. And then at the Montana Bureau of Mines and Geology, there are a number of scientists like Mike Stickney. He does all the earthquake work in Montana, and Jan Gallivo and Jesse Mosloff are these geologists that map faults and interesting geologic structures all throughout Western Montana. there are really cool people that I get to hang out with and learn from. And that's really the main perk of this job for me.
That's fantastic. So, we have some nuts and bolts. How
Okay.
many hours a day do you work, and how often do you work over time? So, I think that's taking into account, your field season versus your not field season.
Okay, so I'll preface this by saying I have an unhealthy work life balance. But that's because I love what I do. So I don't know how many hours, but it defines me. It doesn't burn me out because I enjoy it, right? So I spend, I'm not a guy that is on social media. I don't have X accounts or Facebook accounts. But for the USGS, I am active on those, answering people's questions. I work on making videos about how Yellowstone works and things like that are in addition to my normal job. So, I only get paid for 40 hours a week. I don't get overtime or anything like that. But I work more because I really enjoy it. And the coughing was not meant to be ironic. Um, I I love what I do, and so I'm more about the having the opportunity to talk to people about Yellowstone and do interesting research, and in other places too, in Hawaii and Mount St. Helens, that I find very fulfilling. Um, so that was the question about hours, and it does vary, right? When you're in the field, you work until the job is done, and that usually is you're in the field shortly after the sun comes up, and you're going until the sun goes down. So you just have to take advantage of those days, uh, but usually it's not really a chore. I mean, my job is to be outdoors in a place like Yellowstone. Twist my arm.
I love it. Okay, we have a question. What's the biggest accomplishment in your life? What are you most proud of?
That's a really tough question. I've not really thought about that before. Um, I'm proud of some of the scientific work I've done, but I feel perhaps more fulfilled by some of the public outreach things I've done. And so when I had the opportunity to um, start with Yellowstone, with the Yellowstone Volcano Observatory, I introduced some new products. So, for example, every Monday morning, we do an article called Yellowstone Caldera Chronicles, and it's about some aspect of Yellowstone geology, current activity, research, seismicity, whatever. And I edit all of those articles and I post them online, and I know they're reproduced in some newspapers in Montana and Wyoming, Idaho. Um, and through that, I think I don't even know how many people are reached, but I get a lot of feedback from people. Wow, I didn't know that there was this really interesting geologic structure that I can see right outside my window, because I live in Paradise Valley or whatever. Um, we've done videos, we've done these neat reports that have all this information about Yellowstone. Those sorts of public products that have shared the wonder of Yellowstone, I think I'm very proud of those, because I kind of said it earlier, right? I mean, I can write a scientific paper, and who's going to read it? A couple of my friends, basically. Maybe it's good, maybe it's sort of not. But the idea that I can say some neat things about Yellowstone, give a presentation in Gardner or West Yellowstone, help some of my colleagues write these articles that appear every Monday that can be read by people throughout the region, that's really fulfilling. And so I think probably I'm proudest of some of that outreach that we've been able to do with Yellowstone.
Okay, we're all very much aware of the Yellowstone caldera and we know about the Cascades, but are there any other volcanoes that, like in our region, that maybe are not front and center in our
Yeah,
mind?
yeah, yeah, absolutely. In your region, I'd say the Snake River Plain in Idaho, Craters of the Moon, Hell's Half Acre. And then if you go a little bit to the south, in the southwestern US, uh, especially southern Utah, northern Arizona, and kind of central and northern New Mexico, have volcanoes all over the place. They're sort of out in the middle of nowhere. Not many people would be worried about them. Even if they erupted, it probably wouldn't affect too much, although they might affect some interstates or highways. But there are enough of them out there, and they have these sort of one-off eruptions. They'll form a little cone and then they'll stop, and the eruption might last a few years. The last one in the Southwest was Sunset Crater near Flagstaff, Arizona. That was about 1,000 years ago. And the eruption interval is maybe 1,000 years or so collectively. So when you add it all up, it is about as likely that you would have an eruption somewhere in Idaho or in the southwestern US as you would in the Cascades, except for Mount St. Helens. Mount St. Helens erupts all the time. If you take Mount St. Helens out of the Cascades, there aren't that many eruptions. And so you would be just as likely to have an eruption in the non-Mount St. Helens Cascades as you would somewhere in the middle of New Mexico. Those don't get a lot of attention, and they wouldn't be tremendously hazardous because there aren't a lot of people that live around them. But man, that would be spectacular. I mean, can you imagine if there was a fountain of lava in southern Utah? That would be the biggest tourist attraction in the world. And I'd be right there too. So yeah, there are volcanoes that don't get their due, maybe because they aren't seen as, super hazardous, threatening things, or people sort of drive by them and don't pay much attention to them, but they're there. And it wouldn't shock me if we had a cinder cone eruption in northern Arizona. Yellowstone has not had an eruption in 70,000 years, and that was a lava flow. It wasn't even an explosion. Last eruption in the Southwest was 1,000 years ago.
Wow, that's interesting to think about. Do you have a favorite volcano?
Yes, I do. I feel guilty playing favorites, but I do have a favorite. My favorite is this volcano that I bet no one's heard of. It's called Medicine Lake. It's in northeastern California. It is just to the east of Mount Shasta. And it's a low shield. It's not a real pointy volcano, but it's a low shield. It's got obsidian lava flows. It's got lava tubes. It has this gorgeous little lake. Not many people know about it. It smells good, like with all the trees. And when I'm there, I feel like, man, I'm away from it all. I'm in my element. And I did some of my earliest work at that volcano in the 1990s. So that's always felt like a really special place to be.
Oh, that's great. Okay, this is our last question.
Okay.
And it is, what advice do you have for students who are fascinated by volcanology and are considering a career in the field?
So what I did when I decided this is what I wanted to do is I tried to find, say, a professor who was doing some work and not shadow them, but basically say, hey, are you doing any field work? Can I help you? And this one professor said, yeah, in fact, I'm going to Hawaii in a couple of months. I need a field assistant. Why don't you come along? And I started meeting people, and other opportunities suddenly presented themselves. So I think if it's something that interests you, don't wait for the opportunities to come to you. Go out and get them. The question earlier about, is there an internship? Maybe not formally. Maybe there is not a formal internship at the Montana Bureau of Mines and Geology. That doesn't mean you can't go there and say, hey, I'm really, really interested in this. Is there somebody that needs a field assistant for a week or something like that? I'll carry your rocks or whatever. And the amount of experience you get with that sort of thing it's vital. So look for those sorts of opportunities and put yourself in position to take advantage of the opportunities that come along. And the experiences you get will tell you whether or not you really want to do this for a career, and you'll start developing connections that will help you immeasurably as you explore.
That's wonderful. Michael, thank you so much for joining us for International Careers Week, and thank you to all the students and teachers that also joined us. I want to take a quick second and thank our sponsors, Stockman Bank, the Dennis and Phyllis Washington Foundation, Clearwater Credit Union, and Humanities Montana. Michael, thank you again.
My pleasure. Thanks very much. Take care, everybody.
Thank you. Goodbye.